Okay, combustion reactions. A combustion reaction is any reaction where a fuel is burning, and the gas that supports combustion in our atmosphere is oxygen gas. So O2 is a reactant in every combustion reaction. That means that when you wrote a synthesis reaction of magnesium plus O2 forming MgO, that was also a combustion reaction. But we typically classify those reactions where one product is produced as a synthesis reaction. So commonly then you'll see these combustion reactions have a fuel containing carbon and hydrogen and sometimes other elements reacting with oxygen gas. There's really two opportunities for products here. One is the complete combustion products of carbon dioxide and water vapor, and secondly, we have the incomplete combustion products, which are CO2 and H2O also, but in addition, carbon solid and carbon monoxide. You'll notice here that I use X and Y, so basically they could be any number here to represent the formula of the fuel. And oxygen is the second reactant in both cases, and you see the products listed here. So when there is enough oxygen, so when we have a plentiful supply of oxygen, then the fuel will burn with a blue flame, and the carbon that's present here will have enough oxygen to form carbon dioxide and water vapor. If the oxygen supply is lean or poor, then an orange flame is typically the color of the fuel burning, and it means that there won't be enough oxygen for all of this carbon to convert to carbon dioxide. Some of it will be isolated as just carbon solid, and some as carbon monoxide. Yes, possibly CO2 will be produced, and there's always going to be water vapor. So, keys to complete combustion will have a visual clue of a blue flame when the fuel is burning, and secondly, that there's an oxygen-rich environment. So, burning a fuel outside as opposed to indoors or in a closed environment like a garage with the door closed, these are oxygen-rich environments. And there are certainly rules around bringing barbecues indoors. There's a reason we have to burn those gases outdoors, and that's so that we keep a plentiful supply of oxygen. Now, it's possible that there could still be some carbon monoxide produced when a fuel's burning outdoors, and so it's safe to always burn a fuel outdoors to give us the opportunity to vent that carbon monoxide to the atmosphere. So typically we think of complete combustion products when a blue flame occurs and it's an oxygen-rich environment. Incomplete combustion products, we have the visual clue of the orange flame, okay, and have a look at these four products, right? What will be the other visual clue? The other visual clue of incomplete combustion. Absolutely, the black solid of soot. So this is pronounced soot, like your foot, soot. And the black soot can get into people's lungs and cause respiratory problems. Carbon monoxide is a colorless, odorless gas that will kill you. And so we have, for those of us that have gas burning appliances in our homes, like furnaces or stoves, it is mandatory to have a CO detector on the floors in your home where the appliances are, and also on the bedroom floors. So it's a good idea to have it, a CO detector on every floor of your home if you have gas burning appliances. So carbon monoxide actually binds to our hemoglobin preferentially, so more favorably than oxygen gas does. And so when we're breathing in an atmosphere that has both oxygen gas and carbon monoxide, the hemoglobin will bond with the CO as opposed to the O2. And that now means that CO is what's being taken to our tissues and our brain as opposed to O2, which the lack of oxygen leads to feeling drowsy, perhaps a bit of a headache, and people lose consciousness. And if they're not removed to an oxygen-rich environment, then they risk actually dying. So definitely we prefer complete combustion, and if you do have a gas burning appliance, then it needs to be vented to the atmosphere so that any CO that is produced does get vented to the outdoors. Okay, so to practice now, write balanced equations for the complete and incomplete combustion of ethane. So I've given you the formula here, C2H6. So pause the video and write your reactants, predict products, balance the equation, fill in your states, and then check back with the video. Okay, so you'll see that I wrote the oxygen gas as a reactant in both equations, and then in the complete combustion products, CO2 and water vapor, and in the incomplete combustion products, I added carbon soot and carbon monoxide. So to balance these equations, it's always hardest to balance the element that appears in multiple reactants or products. And in this case, oxygen appears in multiple products. So it's easiest to approach carbon, then hydrogen, and then oxygen. So I look first at the carbon and see it here with 2. So I come over and put a 2 because of the 1 here for C, so 2 carbon. Then I check the H, I see 6 there, so I'll throw a 3 up here, and 3 times 2 will be 6. Now, when I go to balance the oxygen, because I've fixed the coefficients on the right side here, I'll figure out how many I have in total. So there's 4 there, and 3 times 1, there's 3 there. 4 plus 3 is 7. Well, that's an odd number, and I look over here and don't see any oxygen in the fuel, which means all 7 have to come from this O2, and that's not going to work without fractional coefficients. So when that happens, and here's why we balance in pencil, I recommend that you erase everything that you've done and go back to where you started, which was with those 2 carbon. And so instead of leaving a blank in front of the C2H2, I'm going to put a coefficient of 2. I'll just make a comment here. Ethane happens to be a gas, and no, I didn't expect you to know that, so I'm providing that for you. Okay, so now I have 2 times 2. Now I have 4 carbon. So on this side, 4 times 1 would be 4. And I have 2 times 6, 12 hydrogen. So I come over here, and 6 times 2 will be 12 hydrogen. And now 4 times 2 is 8. 6 times 1 is 6. And now I have 14 oxygens, which I can easily then place a 7 to come up with the correct number of oxygen on the left side. Okay, so to balance the incomplete combustion reaction. Now, this is definitely trickier. You can see that we not only have oxygen split now on the right side between multiple products, there's actually 3 products that contain oxygen. We also have carbon split, and that means that carbon's going to be tricky to balance. One thing I can notice though right off the bat is that only having 2 carbon on the left side, I already have 1, 2, 3 carbon on the right side. So definitely this will not stay as a 1. And so I'll try it as a 2 so that I have 4 carbon on the left side. And I notice right now that I have 1 here, 1 here, and 1 here. So really, if I put a 2 in front of any one of those, that would give me the 4 carbons. I'm not going to place that yet because I'll do what I can, what I think to be certain, and then see if I can make, through logical deduction, a more confident move. So next thing I'll look at is hydrogen, and notice that 2 times 6 is 12 there, and I come over and water's the only source of hydrogen on the right side. So 6 times 2 gives me 12 there. So hydrogen's balanced. And what I just did by putting the 6 water is actually fix the number of oxygen from this water. So if I have 6 there, and right now 2 from the CO2, and 1 here from the CO, then I realize that that's actually an odd number, right? 6 plus 2 plus 1, that's actually 9 oxygen, which is not going to work nicely with my even number. But I do have a little flexibility here. I could put a 2 here in order to make this one a 2 for 2 oxygens. And that would actually give me 10, which I could easily throw up a 5 to balance on the left side. So by putting the 2 in front of the CO, did I actually balance the carbon? Well, as I check it out, I've got 1 carbon here. Now I have 2 times 1 from the 2 COs plus 1 from the CO2. So it turns out that coefficients of 2, 5, 1, 2, 1, 6 actually is one possible answer for the incomplete combustion reaction of ethane. You will find with incomplete combustion reactions that we don't always have all 4 products formed. Sometimes it's only 3 of the 4. And even when you do have all 4 products, sometimes there's more than one possible solution. For complete combustion reactions, there is only one correct balanced equation. Okay, and the last thing to point out here is just the idea of the oxygen-rich and oxygen-poor reactions here. Notice the ratio of oxygen to the fuel in the complete combustion reaction is 7 to 2, right? And 7 to 2 is really 3.5. 3.5 to 1. When you check the incomplete combustion ratio, you'll see 5 over 2, which is really 2.5, right? This was our ratio 5 to 2, which is 2.5. So I really have 2.5 to 1. And so what we're seeing here is that the ratio in the incomplete combustion reaction, we needed 2.5 amounts of oxygen for every 1 amount of fuel. And here, for the complete combustion, we need 3.5 amounts of oxygen for every 1 amount of fuel. So you can see that the complete combustion reaction actually requires a greater amount of oxygen compared to the fuel than the incomplete combustion reaction did. And so that supports the idea that our complete combustion reaction occurs in O2-rich environments and our incomplete combustion reaction occurs in the O2-poor environments. Okay, so that's it for combustion.